Okay, so this is your first video lesson. In your table of contents that we put together, at the top you want to put limits by table and graph. The standard is L1 and L2, and then of course page 1. The target for this lesson, of course, is to use a table and a graph to calculate the limit of a function to see characteristics of a function as a certain x value is approached. So we're going to start talking about the idea of a limit. So let's see. So consider the function that we have on top right here. Of course, this is a rational function, rational meaning fraction. That function right there, x cubed minus 8 over x minus 2. Now in Algebra 2 pre-cal, we learned how to factor that. We learned how to find our removable discontinuities. So from the graph, we can see that it definitely has a removable discontinuity at that point when x is equal to 2. We know that too as well because we know our function is going to be undefined when x is equal to 2, since 2 would cause our denominator to be equal to 0. And that's something that we don't have, that we don't want. Okay, so I want to look at what happens as we get really close to that value. Not necessarily at the value, because I know at 2, we have an error. We have that removable discontinuity. But as we get close, so let's say I take 1.9, which is a value close to 2, and plug it into the equation. I would get 11.4. Okay. If I got even closer at 1.99 and plugged that into the equation, I would get 11.94. And then of course 1.999, plugging in, I get 11.994. Okay. So as we get closer to that 2 from the left side, we call that the negative side. Our actual y value gets close to about 12. We don't know that for sure, but we can see the habits in the number from 11.4 to 11.94 to 11.994. Now I want to look from the other side. So from this side, we've determined that it's going to approach 12. I want to see if it's doing the same thing from the other side. So if I plug that 2.1 in, I'm going to get 12.6. If I plug 2.01, I get 12.06. And if I plug 2.001, I get 12.006. So as our x value approaches that 2 from the positive or the right side, we call that the positive side. That means our y value, looking here in that habit, sorry that arrow's ugly, is also going to approach 12. Because these two match, we can say that the limit of f of x as x approaches 2 is 12. So that's kind of how we explain it in written words. Symbolically, mathematically, we would say that the limit as x approaches 2 of the function f of x, we can either write f of x or we can write the actual function in there, is actually equal to 12. We know that it is not, the function itself is not equal to 12, but the approach and the limit is equal to 12. So that's going to be a really different mode of thinking when it comes to calculus and limits, because we don't want to know exactly what happens. We want to know what the habit is approaching, what's happening as we get really close. Not at, but really close. Okay. So kind of the way I wrote the last one, just kind of a general idea, says the limit notation, the limit as x approaches a of f of x is equal to L, is read, the limit of f of x as x approaches a equals the number L. The limit equals L, not the function. Okay, so really the informal way of thinking of a limit is what's happening to our y value as x gets really close to a certain number, a certain independent variable. So now there's 4 ways to actually calculate a limit numerically, which is what we just did on the previous. We looked at the table, graphically, which we kind of did at the same time, analytically and algebraically, which we know in mathematics is the best way to do anything, and of course written using correct math notation. So the words here is our written piece, the explanation of what that statement means. Okay, so let's look at 2 other functions. I'm going to look as x approaches 1, so we can see there, right there in our table, that we have values that are approaching 1 from both the left side and the right side. So I want to see what's happening to my y values as I approach this 1. If I take 1 and plug it in, I'm going to get a 0 in my denominator again, so there's going to be an error. I don't know if this is a hole, an asymptote, a jump. It can be some type of discontinuity. I don't know which type it is yet. So I'm going to see what's happening in my table. So if I take 0.9 and plug it in, I'm going to get negative 5.3. Okay. If I take negative 0.99, I'm actually going to get negative 50.25. Now that's a big jump in value. I mean, it is decreasing because it is increasing on the negative side, but that's a big jump. Those two numbers are not very close. So let's look as we get closer if there's still that jump happening. 0.999, if I go ahead and plug it in, I'm actually going to get negative 500.25. 0, sorry, ran out of room. So really the values are not approaching a specific, they're just really increasing. And if I got even closer, 0.999, my value is probably going to be about negative 5,000. So as I approach that 1 from that negative side, that left side, my y values are actually approaching negative infinity. They're getting larger. And the closer I get, the larger that value is going to get. Okay, now let's look at the other side of 1. If I take 1.1 and plug it in, I'm going to get 4.8. If I take 1.01, I'm going to get 49.75. Now, that's kind of the same thing as the other side. So I want to see what happens when I put 1.001. So 499.750. Sorry, my chicken scratch right there. So as I approach from this side, the positive side, my y values are approaching positive infinity. Now, infinity is not a value. And on the previous page, I said a specific y value. Because of the fact that infinity is an idea and not a value, we actually would say that this limit does not exist. And the reason for it not existing is because it's infinite. Okay, so those two things kind of mean the same thing when we talk about limits. If we say that the limit is equal to infinity, that really means that the limit does not exist. What's happening graphically on this graph, if we think about it, if we look at it and actually graph it, we're actually going to have at 1, let's say this is 1, if we think of our values getting larger as we approach that, that means we have an asymptote, which means our function goes to positive infinity, negative infinity. So our graph actually looks something like that. Of course, there's going to be another asymptote on this side because of the factoring of x squared minus 1. Okay. So that's one thing that could happen with limits. One thing, we can get a number like we did in the first example. Next thing, we can get an infinite value or an unbounded limit, which means that our limit does not exist. So that's one of the reasons why a limit fails to exist right there, is because it's infinite or unbounded. So let's look at the next one, the absolute value of x minus 1 over x minus 1. If I plug in a negative or 0.9, I'm going to get a negative 1. In fact, I'm going to get a negative 1 everywhere here except at 1. I'm actually going to get an error. Because again, if I plug in 1 to my function, I'm going to get 0 in my denominator. In fact, I'm going to get 0 over 0, which is a huge problem. Okay. Now 1.1, if I plug that in, I get 1, 1, and 1. So as I'm approaching from the positive side, my y value is approaching positive 1. As I'm approaching from the negative side, my y value is approaching negative 1. These two things are not equal. They are a value, but the fact that they're not equal also means that this limit does not exist. They have to be coming to the same value in order for it to exist from the left and the right. And the reason why this one is because there's actually a jump in this graph. So if we look at this graph, we actually get at 1, so at 1 there's going to be a jump. And at 1 it is not defined. So that's kind of what this graph looks like, where this is 1 and this is -1. Okay. So the idea of approaching it from the left, yes, and approaching it from the right, sorry I got those two things backwards, we can have a one side, what we call a one-sided limit, where we're just looking at either the left or the right side. That limit would exist, but because we're not looking at it with direction, that limit's not going to exist because it doesn't come to the same point or the same approach, the same y value. Okay, so let's talk about the idea of, and I think I have these out of order. I'm missing a slide. So I'm going to prop in a slide really quickly. I'm missing one here. So on the next part of your examples, you have an example that says the limit as x approaches 3 from the positive of g of x. I'm sorry that it was missing one of my slides. And you have the limit as x approaches 3 from the negative side. Okay. And the graph looks like this. Of course, you're not writing this in because you have an actual graph on your paper. So this is 3 right here, and this is what we're looking at. So there's an open point here. It's kind of a parabola here, and then closed point here, and just a linear function. So at this value, I know it's a little bit off, and that's okay. That value was 2, and at this value, -1. Okay, that is a terrible graph, and I do apologize for that, but you're going to get the point in a minute. So I'm going to choose a highlighter down here. When we talk about, sorry, I'm going to go back to a pen. When we talk about 3 from the positive side, that means we're approaching from the right side of the value. That is not a pen. From the right. Oh my God, I cannot write today. Okay, so that means we're approaching from the right. That little plus sign is not the value of 3, it's the approach. If we're talking about the negative, that's the left side of that x value. So what I'm going to do is I'm going to take a highlighter, and I'm going to actually highlight at x equals 3, just a vertical line right there. So that vertical line right there represents what it is I'm trying to approach. Okay, so I'm going to approach it from the left side of that line and that right side of that line. So first the right. So we say positive because if we move this way on the graph, we get more positive numbers, versus moving this way on the graph, we're going to actually get negative numbers. So this is the positive side right here. Okay, and this is the negative side. So as I'm approaching, what is my y value approaching? Well, my y value is approaching 2. Let's not do that. Let's get a pin. There we go. Okay. As on the left side, oh my God, I'm putting it on the wrong spot. Ignore that last thing. It should be here. Right side. Right side, positive 3, or 3 from the positive side, so 2. If I'm looking at the negative side, that means I'm approaching from the left of that line that I drew in, that horizontal or vertical line. So as I'm approaching, I'm on my function, and that's important. My y value is actually approaching -1. Okay. So that sign that's behind the 3 represents which side of 3, x equals 3, am I approaching. And if I think about that horizontal or that vertical line, that's our x equals 3 line. So this right here is our x equals 3 line. If we were to graph it, that's what it would look like. Okay, so we're looking at the specific y value as x approaches. Okay, so let's look at another graph, the graph that I actually have in here. This might make a little bit more sense. Now, in order for a limit to exist, our function does not have to exist at that value. It has to exist around that value, and that's an important thing. Okay, so let's look at a limit. So the first one I'm going to look at is, of course, number 1. And it says a limit as x approaches 2, and it has a minus sign on there. So what I'm going to go is x equals 2, assume that these go by 1, and I'm going to draw an actual line, just like I did in the previous problem at x equals 2. That's my x equals 2 line right there. So this is x equals 2. Now, if I'm going from the negative side, that means I'm going from the left side. I have to be on a function to approach a value. Okay, so I have to be on it. It's like a railroad track. As I'm approaching, there's an open point there, but that's okay because it's not about what the function equals, it's about what the function approaches, gets really, really close to. And I would say that is getting really, really close to y is equal to 4. So my limit on that side. If we look at the next one, number 2, x approaching 2 from the positive side. So positive side meaning the right side of that line. So as I'm on that function, I'm approaching that exact same value, that y is equal to 4. So my limit from the approach is y equals 4. The next one, number 3, says x approaches 2 without direction. And what that means is that I have to come from both directions, the left, the negative side, and right, the positive side. And both of those have to approach the same thing. But because both of these were equal to 4, I know that my limit without direction should also equal 4. Okay. Now, when I'm talking about the function itself and not the limit, this is the only time that whether it's an open point or closed point matters. If it's an open point or closed point, that doesn't matter for limits, but it does matter for the function because that's about the quality of a function. So I'm looking for some closed points. So at x is equal to 2, you'll see that you have a closed point right there. So that's where my function is defined. Not my limit, but my actual function. So I would say that my function is actually -1. The limit and the function do not have to be the same. It helps if it is, but it doesn't necessarily have to be. And what that means for us in here is if our limit and our function are not the same, that means our function is not continuous. And that's going to be an important aspect of this class. Okay, so let's look at the next one. What I'm going to do is look at the value that I want to approach. So x is equal or approaching -2. So the first thing I'm going to do again is go at -2. I'm going to drop in a line, just like I did with the previous problem. Okay, so that line represents x is equal to -2. So what I want to do is look from the negative side, so the left side. So as I approach that line that I highlighted, my y value is actually approaching a +2. Remember, that's my y value. As I approach from the opposite side, my y value is approaching 0. Now, without direction, because my left side and my right side are not equal, that automatically means that my function does not exist. What I want to do is anytime I say my function does not exist, I want to state a reasoning for it. And that means there's a jump. If my left and my right side are not equal, that's because there's a jump in your graph. Again, another sign of discontinuity. So the limit has to exist for it to be continuous. Now, if we're evaluating f of -2, again, this is the only time I'm looking for those closed points or those solid lines. because I want to know the equality of the function, not the approach. So if I look at -2, again, that highlighted line that I have up there on the left, I can see that the close point is in fact at 0. So now what I want to do is I'm going to erase and give us some room up here so we can kind of clear out our graph so we can look at our next one. Okay. So the next one, again, the first thing I'm going to look at is as x approaches. So x is approaching 5, so the first thing I'm going to do is go drop in a line. So 1, 2, 3, 4, 5, that's here. And this is just to help you visually till you get used to it and you don't need that highlighted line. So that's my x is equal to 5 now. Negative, I'm moving from my left side. So my y value is approaching. That is a solid line, so there is a point there. So I'm just going to make it a little darker so we can kind of focus in on it. So as I approach from the left, my y value is 0. As I approach from the y, or from the right side, my y value is also 0. And because my left and my right are the same, without direction, should also be the same, just like our first example on the left here. Now, f of 5, this is where I'm looking for those solid points. And that was the purpose of me putting in that solid point to kind of focus. And that's also 0. Anytime these two are equal, that means that your function is continuous. The limit and the function being equal makes it a continuous function. Okay. So we've talked about 2 times our limit fails to exist. There are actually 3 times. So here's some graphical representations of that. The first time your limit fails to exist, of course, is anytime you have a jump discontinuity. That means your left does not equal your right. Okay, left limit, to be more specific. Okay, just like we had in the previous example. Okay, the second reason, again, that's one we already knew that we have a vertical asymptote, so I'm going to actually put that in. It is very important that we say vertical asymptote. Okay, that means that our limit as x approaches this a value, whatever that a value is of the function, is going to be equal to either positive or negative infinity. Okay, that means our values around, as we get closer to that x value, are getting really, really, really large. The closer we get, the larger the value. And then the last one is what we call an oscillating function. Now from pre-cal, we've learned a couple of oscillating functions like sine and cosine. Those are oscillating functions because they go up and down. They have a bound from top and bottom. But when we talk about this type of oscillation, that means that as we get closer and closer, let's say the 0 here, we can't really see what's happening because of the fact that it's bouncing so much. The oscillating function is the most rare one, and it really most of the time only happens with trig, sine and cosine, like the idea of sine of 1 over x. So if this is our function. So the limit as x approaches 0 of this function would not exist because we wouldn't be able to tell exactly what value is approaching, and the closer we get, the more confusing it can become. Okay, so first thing I'm going to do tomorrow is look at this oscillating function, and I'm going to open up with a type of function that looks like that before we move on, because there's a difference between the oscillation up at the top and this oscillation right here. This is okay. This is not okay.